Welcome everyone. All right, here we go. Our very first lesson. And we're getting into it. We're introducing the idea of limits, and specifically limits using graphical and numerical methods. So by the end of this lesson, what are we going to be able to do? Well, you'll be able to find the one-sided limit of a function using both graphical and numerical methods. And you'll also be able to use these one-sided limits to determine what we call the overall limit of our function. All right, so let's start, let's ease into this a little bit. How do we read the graph of a function? Hopefully everyone knows how to do this. But let's just review, because sometimes the easy things are the most difficult. So let's review. How do we read the graph of a function? So here we have this function y equal to g of x. And there's a little bit of something going on here. All right, let's look at g of 1. Let's evaluate g of 1. All right, so how do we do it? Well, the x value here, so this number inside the parentheses, this is telling us the x value to look at. So here, it's telling us look at x equals 1. All right, so we go to the graph of our function here, and then we find the x-axis. Here we go. Here's our x-axis. Find the number 1 on that x-axis. And then we look up. Sometimes we look down, but in this case we're looking up until we see our function. And then we identify the point on the graph at x equals 1. So here we go. We've identified that at x equals 1, there is our point. Now what are the coordinates of that point? Well, it looks to be, we're kind of estimating here, but the x-coordinate is 1. We know that. And I might say the y-coordinate is maybe 0.75. So I might say the coordinate for this point right here on our graph is 1, 0.75. So since we're looking at x equals 1, the number inside our parentheses here, the actual value of our function then is 0.75. So when we identify a point on the graph, the number in our parentheses is the x-coordinate, and then the actual value of our function is the y-coordinate. So x is the number we're plugging in, y is the number that we're getting out for our function. All right, so for here, we're looking at, we want to evaluate g of 4. So this tells us, look at what's happening at x equals 4. All right, so we find our x-axis, we find 4 along our x-axis, and then we look up, we look down until we see our function. In this case, we kind of read up, and there's our point right there. So we identify, well, what are the coordinates of that point? We know the x-coordinate is 4. And then we read over to our y-axis, and it looks to be about halfway between 2 and 3. So again, just estimating here, but I might say that's about 2.5. So the actual value of our function then, we say, is 2.5. The x-coordinate is where we're looking, and then the y-coordinate is the height of the function. So you might think of our y-coordinate as the height. It's helpful to think of it like that. So at x equals 4, the height of our curve is 2.5. We're 2.5 units above this horizontal axis. All right. Let's get a little tricky. Let's evaluate in part C. Let's see what happens at x equals 2. We want to evaluate g of 2. And what do? Well, we find our x-axis, we locate x equals 2, and then we look up and down to see if there's any points on our graph. And what we're seeing here is we have these open dots. They're kind of not filled in. And so we're going to see this quite a bit in a lot of the examples we do in this course. And so it's more of just a matter of convention here. When we have a filled in dot, so I use these filled in dots over here. When it's filled in, what does this mean? it means the point is on our curve. So it means if the dot is filled in, it means we want to include that point. It's actually on our graph. If it's an open dot, where we don't fill it in, then that means the point is actually not on our curve. So filled in dot means that's actually there. So that point is actually there on our curve. That's why I filled it in. The open dot means it's not. So how we read this is the graph of our function is getting really close to this point, but it never actually reaches that point. That point is not on our graph. Same thing with over here. On the right side, the curve is getting really close to this point, but it never actually reaches that point. That point is not on our curve. So the fact that there is no filled in dot at x equals 2, we can look up and down all we want, and there is no filled in dot or part of the line at x equals 2. So this is undefined. It's actually not on our graph. A little tricky there. So you can think of when we have these, normally when we graph a function, it's like a line like this or a curve. What you can do is you can think of every single one of these. You can think of that line as just being a collection of all these different points that are filled in. And if you were to draw each of those individual points, it's going to have so much overlap in your drawing there where it just kind of gives you this look of a curve or a line. So just think of every little point here on this line segment as being a filled in dot. And when you fill in enough of them, you get what looks like a curve. All right. So let's talk about what's actually happening there at x equals 2. And this is really going to introduce our idea of limits. So going back here, there's something different at x equals 2. Something's happening there, something interesting. The left side is doing something different from the right side. And so we want to be able to talk about that. And we want a good notational system that allows us to talk about that. And so what's going to help us is this idea of limits, and more specifically, one-sided limits. So there's this interesting behavior at x equals 2 here. And so we want to identify, and this graph is slightly different because this one actually does have a filled-in dot. So this one is slightly different than the one we just looked at. But first of all, what point does the left side of our curve approach near x equals 2? All right, so here's our curve. We identify x equals 2. So here's x equals 2. And I can do that a little better. There we go. All right, so let's look to the left of x equals 2. So that means we're over here. We're on the left side. And let's imagine just kind of starting over here on the left. And just imagine walking along this curve, and we're going to get closer and closer to x equals 2. So what we're doing here is imagine that we're starting, our inputs are starting somewhere over here on the left. And we're looking at the corresponding point on our curve. So as these input values get closer and closer to 2, what is the actual corresponding point on the curve doing? Well, it's moving this way. And it looks like we're getting closer and closer to this point right here. So what are the coordinates of that point? This point has coordinates 2, 1. The x-coordinate is 2, the y-coordinate is 1. This point is not actually on our curve, though, but we're getting closer and closer to it. All right. What about on the right side? So it looks like we're getting closer and closer to the point on the left side, 2, 1. Now what about on the right side? Now on the right side, Again, we identify x equals 2 here, and we want to start to the right. So we're going to start over here and just pick some input value, and just imagine this input value getting closer and closer to 2. And we want to see, well, what does the corresponding point on our curve do? So here's our corresponding point. And so as these input values, as we kind of get closer and closer to 2, the curve, if we walk along our curve here, what is it doing? Well, it looks like it's getting closer and closer to this point right here. So what are the coordinates of that point? Well, that is 2, 2. So on the right side, it looks like we're getting closer and closer to this point 2, 2. So on the right side, it looks like our curve is getting closer and closer to this point. And so we want some way to kind of notationally to talk about this, the left side and the right side. And as we're going to see, it's with limits, and in particular one-sided limits. So for this left side notation, what we're going to write is the limit as x approaches 2, and then we're to indicate that it's the left side, we're going to put a little minus there. So the limit of our function g of x as x approaches 2 from the left. And what is this limit equal to? Well, it's equal to the y-coordinate of that point that we're getting closer and closer to. So the limit on the left, if we go back to our graph here, imagine standing on our curve and imagine just walking closer and closer to this point. Well, the y-coordinate of that point is 1. So that's our y-coordinate there. All right. Now what's the notation that we use for the right side? Well, over there, we're going to use this LIM to denote that we're talking about a limit. We're kind of getting closer and closer. We're seeing what happens to our function as the input gets closer and closer. And we're letting our input values get closer and closer to 2. So that's what we're doing over here on the right. We picked an input, and then we're just seeing what happens as we get closer and closer to 2. So we kind of move this point from the right side closer and closer to 2. And we're seeing what happens to the point on the curve. So imagine just being at this point, and we're just walking along the curve, and we're getting closer and closer to this point right here. So we say the limit of our function g of x as x approaches 2 from the right. That's what that little plus means, is we're on the right now. And we say that this limit is equal to the y-coordinate for that point we're approaching on the right. So in this case, 2. All right. So this is the idea for graphical limits. We're looking at the left and the right sides. All right, so the definitions. Here's the formal definition along with the notation here. So for the left side limit, means what are we doing? We're looking at input values x that are slightly smaller, and we're letting those input values that are smaller get close to that number a. And we're seeing what happens to the output value of our function f of x. And in the case of the last example, it's getting closer and closer to a specific number L. So we say if this is the case, if we have these smaller input values x that are getting closer and closer to the number a, and the output values of our function f of x are getting closer and closer to the number L, the way we indicate a left side limit is with this notation here. The limit of f of x as x approaches a, we use a little minus there to indicate we're on the left side, and we say that this limit is equal to whatever number we're approaching. So the key thing here in this definition here for the left side is x is approaching a from the left. We use this minus sign to indicate left. Now for the right side, what's happening is we have larger input values, and we're seeing what happens as those larger input values get closer and closer to the number a. And we're seeing what happens to our function. So the notation that we use here to denote the right side is x is approaching a, and we have a little plus there. And that plus means we're just slightly bigger. So that's how you can kind of remember the different notations. Is think of a number line. And we're interested in what's happening around x equals a. So we have to the left of x equals a, and we have to the right of x equals a. Over here on the left, these are all the values that are smaller. And over here on the right, these are all the values that are larger than x equals a. And on the left side, this is where our input x is less than a, if it's smaller. And on the right side, this is where x is greater than a, it's bigger than a. So you can think of it as over here, the a minus, the a with the superscript of a minus there. What does that mean? Well, it means we're close to a, but we've subtracted a little bit. So the a with the minus there means we're close to a, but we've just taken a little bit away. We're slightly smaller. And the same thing with the a with the plus. How can we remember that? Well, it means we're near a, or we're close to that number a, but we've added on a little bit more. So we're slightly bigger. If we add a little bit on, then we're going to be slightly bigger. So if we're on the left, we're slightly smaller. We're close to a, but we've subtracted a little bit. If we're on the right, we're close to a, but we've added on a little bit. So it's kind of help you remember this notation. All right. So with that, we have a left side limit, we have a right side limit, and we can put the two sides together and we can talk about the overall limit. So, or just limit. So, what does our definition say here? Well, we say that the number L is the limit of the function f of x as x approaches a, provided our function f of x can be made arbitrarily close to that number L for all x sufficiently close but not equal to a. And in that case, we use this notation. The limit of f of x as x approaches a is equal to L. And really just notice here that there is no plus or minus. It's just x arrow a. X is approaching a. X is getting closer and closer to that number a. And so the fact that we don't have a plus or a minus, we're not talking about a left or a right side limit here, is that this overall limit is regardless of the direction. So it's regardless of how we approach a, the direction. So we could be talking about the left, the right, or maybe we're bouncing back and forth from x values on the left to x values on the right, back and forth. And we're still seeing they're kind of getting closer and closer to this one common value. Now one thing to kind of keep in mind here with this definition is that when we talk about the limit, it's only as the inputs are getting closer and closer to a. We don't actually consider what happens directly at x equals a. So for limits, it does not matter what happens directly at x equals a. And we'll see that in the next couple examples. So just a few notes here when we look at this definition. So the overall limit kind of throws out the directions. So left, right. We're just approaching A. Could be from either direction. And then also for limits, it doesn't matter what happens directly at that x value, x equals A. Now, this overall limit, though, it is related to our left and our right hand limits. And so this is going to be important. We write the limit of our function f of x as x approaches a is equal to L if both the left hand and the right hand limits are equal to L. So our left hand limit as x approaches a from the left has to be equal to L, and our right hand limit has to be equal to L as well. So these both have to be equal. So the left-hand, right-hand limits, if we kind of put them together, and if they're both equal to the same number, well, then we say the overall limit, the limit of f of x as x approaches a, is equal to L as well. And so there will be cases where these left and right-hand limits are different, and if that's the case, then we say that this overall limit does not exist. So in order for us to talk about just this regular limit, the left and right-hand limits have to be equal to each other. And if they're not, well, then this thing does not exist. And we use DNE as sort of the abbreviation. All right, so let's try a few more examples here, just to get a little practice. So let's look at example 1. We're going to use this graph to compute the limit of the function g of x as x approaches 2. So this is the overall limit that we're interested in. And so how to actually calculate this is we're going to look at both the left and the right hand limits and see if they're kind of getting closer to the same value. So the first thing, let's try the left hand limit. So let's start with the left. So that means we're going to do the limit of our function g of x as x approaches 2 from the left. So we're using that little minus sign to indicate we're approaching from the left. And we're going to calculate this limit. All right, so let's go to our graph. We find x equals 2 is right here. So let's just identify that. Here we go. And now we're going to look to the left. We're going to look over here. And let's pick a point on the left, and what we're going to do is imagine just moving that point closer and closer to x equals 2. So imagine just sliding this point, walk it closer and closer to x equals 2. And we want to see, well, what's going on actually on the curve? What's going on with the graph? So if we find the corresponding point on the graph, we're going to walk along here. And it looks like as we do that, whoops, we're going to get closer and closer to this point right here. So what is the coordinates of that point? Well, that is 2, 1. And so if we look at this input value that's on the left, and if we move that point closer and closer along our curve, it looks like we're getting closer and closer to this point right here, and the y coordinate is 1. So we say that our left side limit, our left-hand limit here, as x approaches 2 from the left, is equal to 1. So again, this is just the y value. This is our y coordinate of that point. All right, well, let's try the right side. Let's do the limit of our function g of x as x approaches 2 from the right. So we use this little plus sign to indicate that we're on the right side. We're looking at the right side limit. All right. So again, just kind of identify where x equals 2 is. Pick some input value, somewhere on the right. And then just imagine we're going to move this. We're going to see what happens as this input gets closer and closer to x equals 2. And so we want to find the corresponding point that's actually on our curve. And if we kind of walk along our curve here, it looks like this point, as it moves, is going to get closer and closer to that same point, 2, 1. So it looks like we're going to be walking closer and closer to that same point. And so the y-coordinate is 1. So we say the right-hand limit, or the right side limit, is equal to 1. The limit of g of x as x approaches 2 from the right is equal to 1. All right. Now, one thing to note here is that this function is actually undefined. At x equals 2. But that's perfectly okay. Doesn't matter what happens directly at x equals 2. We're only talking about what happens as we get closer to x equals 2 from either side. But the fact that this is undefined at x equals 2 doesn't matter when we're talking about limits. So since the left and the right-hand limits are both equal to 1, well then the overall limit, the limit of g of x as x approaches 2, is also equal to 1. And again, that's because our left-hand limit is equal to our right-hand limit. So the fact that these two one-sided limits, the left and the right, both exist, they're both equal to a number, the number 1, well then our overall limit is also equal to 1. All right, let's try another one, just for the practice here. Example 2. Here we go. We have the graph of the function y equal to g of x. And we want to use this graph to calculate the limit of g of x as x approaches 2. So let's kind of look at the left hand and the right hand limits. And we've kind of done this one already, but let's try it again. So let's start with the left side limit, the left hand limit. So to calculate the overall limit here, we need both the left and the right to figure out, what the overall limit's going to be. So let's start with the left. So x is approaching 2 from the, but with slightly smaller values. So again, just kind of identify where x is approaching. So we want to get closer and closer to 2. Identify the left side. So here we go. Pick a point over there. Pick a input over there, find the corresponding point on the curve, and then we're going to see what happens as we move closer and closer to 2. So the point on the curve is going to move closer and closer to this point right here. And this point has coordinates 2, 1. So the y-coordinate is actually the value of our limit, the left-hand limit here. So our left-hand limit is equal to 1. Now, if we do the right side, the limit of g of x as x approaches 2 with slightly larger values, so it means we're on the right. So again, pick some input value that's to the right of 2. And what we're going to do is we're going to find the corresponding point on our curve. So here it is. And we're just going to imagine walking along our curve, and we're going to let the x-coordinates get closer and closer to 2. So we're going to let our x values move closer and closer to 2, and we're going to see where does this point go? It's just going to walk along our curve. And it looks like we're getting closer and closer to this point right here. So that point has coordinates 2, 2, and it's the y-coordinate. That's the actual value of this limit. So this limit is equal to 2. Now the left hand and the right hand limit, both of these limits exist. There's numbers here, but they're not equal. So the overall limit, the limit of g of x as x approaches 2, does not exist because these are different. So you want to be able to justify this. So why does this not exist? This is important. Why does this limit not exist? And the reason is the left-hand limit does not equal the right-hand limit. We need those two to be the same. And we don't have that here. Now, notice that this function is actually defined at x equals 2, but that played no consideration in our calculations for these limits. So this function is actually defined. So there is actually a point on our curve here at x equals 2. So in example 1, here is a function, the limit exists, but our function's actually undefined at x equals 2. Didn't matter. We could still talk about the limit. What happens as we get closer and closer to x equals 2? What happens directly at x equals 2 doesn't actually matter. Same thing in example 2. We're just talking about what happens as we get closer and closer to x equals 2. Doesn't matter what actually happens directly at there. In this case, this function is actually defined. Didn't matter. All right. So that's the idea for graphical limits. Now, we also want to be able to kind of investigate limits numerically. And that's usually with a table of x values and then their corresponding function values. So normally it's one column of x values and then a column of function values. All right, so we want to talk about what happens as we get close to or we get near x equals a. So what is a list of possible x values we could use to investigate x getting closer to 2 from the left? And we want to do this numerically. So what's a list of x values that are going to be close to 2 but just slightly smaller? And you know, one example of this, by no means is this the only list that we could come up with, but we might have something like 1.9, 1.99, 1.999, one more, 1.9999. Sure. So as we read down this list, what's happening? The values here are close to the number 2, but they're all just slightly smaller. And as we read down this list, what are these numbers? Well, they're getting closer and closer to the number 2. So as we read down this list, the number down here is much closer to the number 2 than the ones that came before. So as we go down this list, the values here are getting closer and closer to the number 2, but they're all slightly smaller. All right, so this is just one example, but there's other ones. We could have done like 1.8, 1.9, 1.98, you know. So you could come up with all sorts of different lists. You know, this is just one example of that. Now, what about something that we could, a list of x values that we could use to investigate x approaching 2 from the right? Well, you know, again, there's all sorts of possibilities, but one example could be 2.1, 2.01, 2.001, 2.0001. So as we read down this list, all of these values are getting closer and closer to the number 2, but they're slightly bigger. They're slightly larger. So as we read down this list, x is getting closer to 2. Now, for the left-hand limit, we can see these are all smaller. They're all slightly smaller. They're close to 2, but slightly smaller. And as we read down, they're getting closer and closer. And for the right-hand limit, these are all slightly larger. So again, they're getting closer and closer to 2, but they're slightly bigger. And so what we want to do in investigating a limit numerically is we look at not only those list of x values, but then the corresponding function values. And we try to identify a pattern there. All right, so let's look at example 3. We're going to compute the limit of the function 3x minus 5 as x approaches 2. And we're going to do this limit numerically. And so we see here that we're interested in x approaching 2. And so to talk about x approaching 2, we want to think about, well, what is the left-hand limit doing and what is the right-hand limit doing? So we have a table for each of those limits. So we have a table for our left-hand limit, and we have a table for our right-hand limit. So these are all the x values that are slightly smaller than 2. These are all the x values that are slightly bigger than 2 that we're going to use here. And so what we do here is we take each x value and we plug it into our function. So our function here is 3x minus 5. So as an example, let's see how we came up with, I don't know, this value right here. So our function is 3x minus 5. And what we're going to do is we're going to take this x value, 2.01, and we're just going to plug it into this function. So we get 3 times 2.01 minus 5. And what is that? It's 6.03 minus 5, which is 1.03. So that's how we came up with this value here. So, and that's how you can do the rest of these. Take each of these input values and just plug it into the function, in this case 3x minus 5, and just record what the result is. All right, so let's look at this left-hand limit. We came up with, we cooked them up. You know, you might have used different ones, but we cooked up these x values that are getting closer and closer to the number 2. So as we read down this table here, we see that x is approaching 2 from the left. They're all slightly smaller. And we want to see, well, what does f of x do? So as we read down, it looks like f of x is, you know, we have 0.7, then we have 0.97, then 0.997, then we have 0.9997. It looks like these values are getting closer and closer to the number 1. So it looks like f of x is getting closer to the number 1. So what this is telling us numerically is that the limit of the function, let's say 3x minus 5, as x approaches 2 from the left, is equal to 1. So x is approaching 2 from the left. We see that here. We have our function, 3x minus 5, and then it looks like as we read down this table, our values are getting closer and closer to the number 1, and that's what we record here. Now for the right-hand limit, we come up with our x values, our list of x values. We plug them in, see what the corresponding function values are, and then we just try to see if we can identify a pattern here. So as we read down, looks like x is approaching 2 from the right. And then we see what the corresponding function values look like they're doing. We start with 1.3, then we go to 1.03, then 1.003, and then 1.0003. And again, on the right side, it looks like we're getting closer and closer to the number 1. So it looks like our function values here are getting closer to 1. So we say our right-hand limit, limit of 3x minus 5, as x approaches 2 from the right, is equal to 1. And so because both the left and the right-hand limit are equal to each other, we can say that this overall limit then is equal to 1 as well. And again, that's since the left-hand limit is equal to the right-hand limit, and both are 1. So this is how we would calculate a limit numerically. We would produce these table of function values. Now, we might have used different x's for the left and for the right, perfectly fine, but we probably would have seen a very similar type situation going on. All right. Let's try one more example. Example 4, we're going to calculate this limit numerically. So our function here is 3 plus x over 9 minus x squared, and x is approaching negative 3. So since we're talking about just an overall limit here, x is approaching negative 3, we need to think about the left hand and the right hand limits. So we're going to look at the left, we're going to look at the right. And so if we're going to do this numerically, it's up to us to decide, what x value should I use? So we want to find x values that are close to, in this case, negative 3. And for the left, slightly smaller. So what's smaller than negative 3? Well, negative 3.1 is smaller. It's close, but slightly smaller. Negative 3.01, negative 3.001, negative 3.0001. These are getting closer to negative 3. So as we read down this list, what's going on? Well, x is approaching negative 3 from the left. So we're getting closer and closer to number 3, but all of these values are just slightly more negative. They're slightly smaller. All right. Well, we also want to, if we're thinking about the right-hand limit, we also want to come up with some x values to use. So as we look down this list here, negative 2.9, that's close to negative 3, but it's slightly bigger, slightly less negative. Negative 2.99, okay, we're getting closer. Negative 2.999, negative 2.9999. So here we're getting closer and closer to negative 3, but we're just all slightly bigger. So x is approaching negative 3 from the right. And so then to figure out these function values, we would take each of these x values and plug them into our function. So our function here is 3 plus x divided by 9 minus x squared. So if we wanted to say, figure out this value right here, I would take negative 3.1 and just plug it into this function, and I've just recorded the result. It's this decimal, 0.1639344. And we would do that for each of these to fill in all these entries on our table here. All right, so once we've filled everything in, we have our inputs, we have our corresponding outputs, we want to identify what behavior is, what's going on here. Does it look like these values are approaching one specific number? And I would say, in the case of this left table, yeah. So notice that we start with 0.16 and then some other stuff. Then if we read down, we have 0.166 and then some other stuff. And 0.1666. So it looks like we're throwing in more sixes here as we read down this list. So as we read down here, it looks like our function values, f of x, are getting closer to the number 0.16 repeating, the 6 repeating there. Now, because of that, we would say the left-hand limit of our function as x approaches negative 3 from the left is equal to 0.16 repeating. Now we want to see what's happening on the right as well. So over here, we go to our first entry, it's 0.16 and then some stuff. Then we have 0.166, and we see something similar happening. Just we're throwing in more sixes as we go. So as we read down this, it looks like our function values are getting closer and closer to 0.16 repeating. So we would say our right-hand limit, the limit of f of x, as x approaches negative 3 from the right, is equal to 0.16 repeating. And because these two values are the same, we can say then for our overall limit, this overall limit is equal to that same value, 0.16 repeating, and that's because the right-hand limit and the left-hand limit are the same. And they're both equal to 0.16 repeating. All right, so this is how we would kind of calculate a limit numerically. We would identify the x values that are getting closer and closer, and then see what the corresponding function values are doing, and see if we can figure out the pattern there. All right, so this gives us a good introduction to limits and left-hand and right-hand limits, but there are a few issues with graphical and numerical methods. So the first issue is they're just estimates. When we read off of a graph, here's a graph of a function. If I were to say, what is the value of this function at 1.5, we can produce a pretty good estimate, but it's an estimate, in the end. So I might say, this function, say this is f of x. If we read off of a graph, we're just estimating, either graph or plugging into a calculator and looking at the decimals. So for this one, I might say, f of 1.5, I might say, okay, this point right here, I might say it's about 0.08, but I might be off a little bit. We're just estimating it. Really, it's just an estimate. Same thing when we have all these different function values. Most likely when you plug negative 3.001 into this function, this is not it. There's other things that we left off here. So this is sort of just an estimate, even when we just evaluate a function. So when we read off of a graph, or when we plug into a calculator, we're getting pretty good estimates, but it's really, in the end, in most cases, it's some kind of estimate. It's not the exact value. All right. So that's one issue, is we're not getting necessarily the exact value. Another thing might be we have a false positive. So if we're kind of producing a table of values here, we might just pick some really unlucky x values. So for instance, if we look at this graph, I might have gotten really unlucky and said, all right, I'm going to pick 1. And what is the point on the graph? Well, the height is 0, so the function value would be 0 there. I might pick this point right here, 0.5, and so far this seems very plausible. 1, 0.5. I might actually do this if I'm doing a numerical table here. And then I also see 0 here. And then as I keep picking, I might have just gotten really unlucky and just managed to hit all these places where the function is 0. So I might conclude the limit of this function is equal to 0 as x approaches 0. And it's clearly not, because what happens here? This is kind of like the sine curve, except we've bunched it up. So there's an infinite number of kind of pieces of the sine curve here all squished together. So what's happening is it's bouncing back and forth between -1 and +1 a whole bunch of times. So this graph here does not approach one specific number. It just keeps bouncing back and forth between a whole bunch, everything in between -1 and +1. So this does not approach one specific number. So this limit actually does not exist for this function. It doesn't approach a 0. Maybe you get unlucky and you pick all of these peaks, and you think the limit is equal to 1. Or maybe you pick all of the low points. You get lucky and you pick all of the low points, and you think the limit is -1. And you could do that for any number in between -1 and +1. So this thing just bounces back and forth forever in between -1 and +1 the closer you get to 0. So it doesn't approach one specific number. So for this function, you might, if you're doing this and you're just coming up with a list of values, you might have just picked some really unlucky ones. So this example, it doesn't exist. But you might be tempted to say it's 0 or 1 or -1, but it doesn't exist. So that's one thing. Another thing that can happen is, we're not looking at the whole function here. We're only looking at these little snapshots of the function, and they might not tell us the whole story. And then one other thing that can happen is kind of a technology limitation. So if we were investigating the limit of the square root of x squared plus 9 minus 3 over x squared as x approaches 0, come up with a very plausible list of x values to plug in. So 0.1, 0.01, so on. What do we have here? 0.0000001, 6 zeros and then a 1 here. So we're getting into some small decimals here. And what happens is there's kind of we hit a limit. We hit if we make the decimals too small, well, then we kind of reach the capacity of the computer or the calculator to do the calculations. And so this is the function here, square root x squared plus 9 minus 3 over x squared. Here's my list of values, and I've recorded. I used Google Calculator. So this is from Google Calculator. You could try this. Open a browser and try this. Try it for yourself. And here's the result for the 6 zeros. So for this entry right here, I plugged it in, and it's telling me that the answer is the function value is 0 there, and it's not. It's not actually 0. But what's happening is it's related to, computer science majors. You're probably going to investigate this somewhere along the way in your career here. But this is involving kind of a rounding error. More of a truncation error. But, whenever we're doing these things, and just in general, eventually you have to round somewhere. And this is going to be true for when you're doing things yourself, or it could be true for kind of these, these type of calculations. But what's happening here in this little example is that this decimal is so small that when we square it, it gets even smaller. So what's happening with the computer is that it interprets this square root of this decimal squared plus 9 is that decimal squared becomes so small, the computer just thinks it's 0. So the way it's treating this when we have this really small decimal is it's treating this square root part as just 0 plus 9, square root of 0 plus 9. And so when we do that, it's really, this is what it's kind of thinking here. Square root of 0 plus 9 minus 3 divided by that decimal squared. So it's kind of, that decimal becomes so small, it just interpret it as 0. So we end up with 0 plus 9. So that's just the square root of 9, which is 3. So this is going to be 0 divided by some decimal squared. So the calculator just says, all right, this is equal to 0. And that's what we're seeing here. So if you make these decimals too small in some cases, you kind of reach the capacity of the calculator to actually work with them. And so that's why we're seeing from this point on, we're seeing all zeros here. The function value is not actually 0. The function values here are not 0. But the calculator is telling us it's 0. So you might reach some point where rounding error or sort of just the limitations of the calculator or computer come into play, and that's what we're seeing here. So that's just another kind of issue to keep in mind for numerical and potentially graphical limits is, we're estimating, we're just rounding, and then, if you throw in too much rounding error, that can cause issues also for calculating limits. So, the graphical and numerical approach, it's a good kind of intuitive understand. It helps us get an intuitive understanding of limits. We're going to see in a little bit kind of how to calculate these limits, something like this. How do we calculate it exactly using more algebraic methods? So we're going to see that in a little bit. All right, so that's going to do it for graphical and numerical limits. Next, we're going to look at, in the next lesson, we're going to be looking at infinite limits. So get ready. We'll see you then. Bye-bye.